Okay. Well, as most people would agree, one of the greatest achievements of mankind was the building up of the Standard Model in theoretical physics. We just listened to one of the founder on theory by David Gross. But now, without experiment, there could not be any interest in theory. And the leading experimentalist in the last 50 years is Professor Sam Ting. And he's going to give a talk about what he did in the November evolution and 50 years of electrons and positron physics. Thank you.
Since everybody's informal, I will be also informal. It's okay. I take out my jacket. Yeah. You can give to the lady there. Professor Yao, Professor Yifan Wang, ladies and gentlemen, I am an experimental physicist. At university, I studied both math. I have 2 degrees, one in mathematics, one in physics. Finally, I decided my ability is very limited. I better stay with experimental physics. So what I want to do today, to share with you half a century of experience in particle physics, working in accelerators on the ground, at DESY, at Brookhaven, at CERN, and on the International Space Station. It has been 50 years since the discovery of a new form of matter. This is the New York Times front page, long front page article on November 17th, 1974. New and surprising type of atomic particle form. So this is the result of a series of experiments. The first experiment is measuring the size of the electron. Modern electromagnetic theory, QED, required that electrons have no measurable radius. That's by Feynman, Schwinger, Terrestrial in 1948. The experiment all agreed well with all, the theory agreed well with all experiments until a 6 billion electron accelerator, Cambridge Electron Accelerator, CEA, produced the most sensitive measurement of size of the electron. So this is the CEA accelerator, has 300 meters, and with the electron inside, that was the highest energy accelerator in the world 50 years ago. It produced 6 billion electron volt light, and on a target, you look the size of the electron. What they found is from the measurement, compared with the model of the electron, 0 radius, there's a deviation at a distance of 10 to the minus 17 centimeter. So the electron has a radius of 10 to the minus 17 centimeter. And this experiment was quickly confirmed by subsequent experiment at Cornell. So 2 experiments show the same result, and people become very excited in the international conferences. This is one of the main research topics. Due to the importance of the results, I decided to redo the experiment with a different method at the German accelerator in Hamburg, Germany. And so this is at that time, very small accelerator complex, and this is my team of few people. Unexpectedly, we found light rays, massive light rays. we found when you have a light ray on a nuclear target, you measure QED, is completely agreement with the QED. Namely, the electron has no radius. But then we found at a mass of 3 particles, one called rho, another called omega, and another called phi, you have a deviation from QED. This is not because the violation of QED, but because a photon suddenly changed to a massive particle with same quantum number, go back to electron-positron. So it's a discovery that light ray and light ray with mass have the same properties. So the second series of experiments concerned light rays and massive light rays. At that time, there were 3. Rho, which is a 2-pi resonance, omega, a 3-pi resonance, and phi, 2K resonance. All of them have a mass about the proton mass. So light ray, a massive light ray, should therefore be transferred into each other. That is the theory. The question is, do they actually transfer into each other? So a large group of experiments were carried out. The most interesting one is the observation of forbidden decay. Omega is a 3-pi resonance. A 3-pi resonance does not go to 2-pi. So you cannot have a final state of 3-pi and 2-pi interfere. But the omega can go to a light ray. Light ray can go to 2-pi. And so there's a very finite chance omega will go to 2-pi. And this was looked by Sternberger and by Glashow, by many, many famous physicists. Never found it. With the precision detector, we indeed found when you measure the pi plus, pi minus spectrum, it is not only rho alone, but the rho omega interference. The third experiment is a discovery of J particle. We learned that photons and massive photons do transform into each other. The question is, why should there only be 3 heavy photons? All have a mass of 1 GeV. Rho has a mass 760, omega has a mass 780, phi have a mass 1 GeV. Why there are no more heavy ones? To go to higher mass, we move to higher energy accelerator. So this is the proposal I made to Brookhaven National Laboratory. Said the best way to search for vector meson is through production experiment of the type proton-proton, go to vector meson, go to E plus E minus. That's because vector mesons are produced by strong interaction, thus a high production cross-section. Second, one can use high intensity, high duty cycle extracted beam. Namely, you can take all the accelerator beam out of the accelerator and put it on your target. And third is the E plus E minus enhancement limits the quantum number to 1 minus, thus enabling us to avoid measurement of angular distribution of decay particles. I stated very clearly, contrary to popular belief, the E plus E minus storage room is not the best place to look for vector mesons. Mesons require continuous variation and monitor of energy of the 2 colliding beams. A difficult task requires almost infinite machine time. Storage ring is best suited to perform detailed study of vector meson parameters once they've been found. So in a Brookhaven experiment, we take 10 to the 12 protons per second from the accelerator on 10% beryllium target. At that energy, the multiplicity is 10, so you have 10 to the 12 particle per second produced. 10 to the 12 is a high number, it's a very large number. After 10 to the 12, the rarest of them all is the E plus E minus pair, which is 1 in 100 million of pi pair. Therefore, if you want a 1% experiment, you need a rejection of 1 part in 10 to the 10. What is 1 part in 10 to the 10? During a rainstorm over Beijing, there are 10 billion raindrops per second to find out which drop is red. Therefore, it's a quite difficult, almost impossible experiment. The experiment was not popular with physics community. Most of the physicists believe the search for heavy mesons was not the most interesting research topic. Few believe such difficult experiment could be carried out successfully. So the proposal was rejected by most of the laboratory. I remember talking to DESY, talking to Fermilab, talking to CERN, and finally the proposal was accepted by Brookhaven National Laboratory. So this is an area view of the detector. Because you have 10 to the 12 particles, so to shield the detector, you need 10,000 tons of concrete, 5 tons of uranium, 100 tons of lead, and 5 tons of soap. 5 tons of soap is to stop soft neutron. I did have some trouble with the government to buy 5 tons of soap, but finally MIT decided to buy it for me. So we developed many very precise detector, and this is a position detector developed by the late Ulrich Becker of MIT. To sort out multiple tracks, you put the proportional wires at 60 degrees apart. Well, 60 degrees apart, you have A1 plus A2 plus A3 equal to B1 plus B2, B3. Therefore, you have a rate of 20 megahertz per second. And when the experiment is over, one of the chambers was put at the Smithsonian Institute in Washington for many years. In the early summer of '74, we took some data in high mass vision, 4 to 5 GeV. However, analysis data show there are very few electron-positron pairs. By the end of August, we tuned the magnet to accept effective mass of 2.5 to 4 GeV. Immediately, we saw clean, real electron pairs. But most surprising of all, most of the electron-positron pair peaked narrowly at 3.1 billion electron volts. A more detailed analysis showed the width is less than 5 MeV. So this was the first data. So I expect the peak at 3.1 GeV taken in August 1974. This is an experiment extremely difficult with an enormous amount of background. How do you know it's not due to instrumentation bias? The way to do that is to lower the magnet by 10%. If once you lower the magnet by 10%, the particle bends to a different part of the detector. If the peak is fake, it was shipped away, but it did not. So the discovery is verified. So on the left, show the graph. The blue area is the spectrum with 100% of magnetic field, and the pink area is when you lower the magnetic field by 10%. The unique property of the J particle is its lifetime is 10,000 times longer than other particles. The significance of this is similar to suddenly discovered in a remote village on Earth, a village where people live to be instead of 100 years to about 1 million years old. And that's why they're quite different. And second, the spectrum is similar to that of positronium. On the left is the spectrum of positronium, on the right is the DESY particle transitions. On November 11th, I telephoned Giorgio Ballatini, a close friend before, the director of the Brookhaven Laboratory in Rome, informed him of his results. So the so-called November Revolution has three publications in physical letters. One submitted November 12th by us, another a day later by Professor Richter's group, another by Ballatini's group in Italy, November 18th. It shows once you know where to look, you can get there quickly. So this is our group, by modern standard, is a rather small group. The discovery of J particle confirmed the existence of charm core predicted by Glacial Mayan, which stated in October 1970, the model featured remarkable symmetry between lepton core. Let me just mention, during the summer when I was doing the experiment, the three people, two of them come to visit me often and try to convince me the experiment is not worth doing. I received a notice of obtain a Nobel Prize on October 18th, 76. A few days later, I got a telegram. I got a many telegrams. The most notable one is from Richard Feynman, whom I got to know quite well. The telegram said, "Congratulations, son, but why do they give prize to guys who discover things that I don't expect and didn't understand? Please don't let the prize go to your head." Meaning, okay, you're getting a Nobel Prize, it's because you have made a contribution in a specific field. Does not make you an expert on everything. This is one of the main reasons I never sign any petitions or public issues which I'm not qualified to understand. So in December 10th, 76 in Stockholm, I received the Nobel Prize, and looking at the diploma of my two daughters. From academician Yifan Wang, I learned tremendous progress in the United States, in China, in Russia, in Germany, and try to study tau charm factories. And this is the luminosity as function here. The highest energy is BEP C2 in Beijing. From Professor Wang, I obtained this graph, the spectroscopy of Beijing spectrometer. When you have 58 million events, you see the graph on the left, and when you become 225 million events, you begin to see the structure. Once you have 10 billion events, you see clearly the structure. And that's really a very nice graph. So up to now, in Beijing, 30 new hadron is discovered, especially from Chang meson production and decays. The fourth experiment is the electron at higher energies at the 46 billion electron volt collider in Hamburg with the positron and electron collision. And this is the beginning of international collaboration in high-energy physics for me. The experiment is called the Mark J experiment. Let me also take this opportunity to acknowledge that we have 5 decades of collaboration with Chinese scientists. After the Cultural Revolution in August 1977, Chairman Deng Xiaoping suggested sending 10 scientists each year to collaborate with me. Since then, many Chinese joined my team and have made contributions well recognized worldwide. And this is the first arrival of the first team of Chinese to the Mark J experiment in Hamburg. At the same time, there's the development of the electroweak theory when the accelerator was built. The first paper, 1960, followed by second paper, Steve Weinberg, and then a final paper by Abdul Salam. In Glasshow's paper, it states the simplest partially symmetric model reproducing observed electromagnetic and wake interaction leptons require the existence of at least 4 vacuum boson fields, including the photons. Namely, there should be intermediate vector boson. At that time, it's just a theory, not much people paid attention. Mark J experiment, as announced by Physics Today, confirmed the interference standard model by measuring the electron-positron to mu plus mu minus. If there's a virtual intermediate vector boson, it decays to mu plus mu minus, and this will introduce a forward-backward symmetry, or measurement as function of theta, shown here, agrees with the electroweak theory, no longer agrees with quantum electrodynamics. Also, an important thing is the discovery of gluon at DESY in Germany. When you have an electron-positron collide, you produce antiquark, quark, and gluon. With increasing gluon energy, you begin to have from 2 jet given to 3 jet divided. And this was announced in the front page of the New York Times as a totally unexpected discovery. And also was announced in the People's Daily in September 5th. Professor H.S. Chen, my former collaborator, recorded this incident and the history because with time, different people sometimes have different memories. The 5th experiment is the electron-positron physics at the highest energy. There are 3 experiments at CERN, which lasted 21 years, with 100 GeV positron collide with 100 GeV electron. And this accelerator have a conference circumference of 27 kilometers. The temperature when the particles collide is about 400 billion times higher than the surface of the sun. And so equivalent to the temperature of the Big Bang origin of the universe within 10 to the minus 11 seconds. So this is a large international collaboration. First time I'm involved in this. I'm from Korea, from China, including Taiwan, including Pakistan, India, most of the countries, United States, and many universities in Europe. So this is a cross-section of the experiment, and the magnet is 10,000 tons, and the container 300 tons, 100,000 channel uranium calorimeter. Both the magnet and the calorimeter come from Soviet Union. And this was the largest collaboration in 70 years history of Soviet Union. So there's Mr. Kai and academician, if I want to, there's reconstruction. We published 300 papers, and 300 people received their degrees. But these 300 papers, one of them is included in the front page of Scientific American, can be summarized in a few words. First, there are only three kinds of electrons: electron, muon, and tau. There are six kinds of quarks: UDS, CBT. This is within the available energy. And electrons and quarks have no size. The radius now is less than 10 to the minus 17 centimeters. Unfortunately, the results are in excellent agreement with the electroweak theory. When the experiment agrees with the theory, what you learn is limited. It's only when the experiment confronted with the theory, you learn something new. So for me, I invested 21 years in this experiment, and it's not a big success. After the ultimate untimely shutdown of superconducting supercollider SSC by the United States Congress, I spent quite some time thinking of my future research. I realized I've spent much of my career in different accelerators. So maybe I should do something new, something I know nothing about, something most people consider impossible. And this is how I propose the AMS. The first cartoon I get from my collaborators is time we face reality. We are not exactly rocket scientists. When we started, we have a very large group. Not a single person has ever done anything in space. No one has any experience. This shows experience is not that important. So let me share with you the current experiment on the space station. Cosmic rays are absorbed by 100 kilometers of Earth's atmosphere, which is equivalent to 10 meters of water. So the property, the charge, energy of cosmic rays cannot be studied on the ground. They are very important experiments, study energy and study distribution. But what is the original property? With the exception of photon, charged particle, you cannot distinguish different nuclei. Measurement of charge, origin, energy of cosmic ray require a magnetic spectrometer in space. So AMS provides precision, long-duration measurement of cosmic rays to study the origin of cosmic rays, physics of dark matter, antimatter, and space radiation. So the Institute of High Energy Physics in Beijing is a founding member of AMS experiment. This photo, which shows H.S. Chen and Yifan Wang and others, is the first meeting at Johnson Space Center in 1994. This is a space version of precision detector normally used in accelerators. And so you have a transition radiation detector, identify electron-positron, 9-layer silicon track, measure absolute value and sign of the charge and momentum. A ring image Jerome curve counter, measure charge and energy. Electromagnetic calorimeter, measure the energy of E plus C minus. Two-time applied counter, measure charge and energy, and the magnet identify sign of the charge and momentum. At first, we built a superconducting magnet. Then after the magnet is finished, we found the magnet fit to design value with superfluid helium of 1.8 K and duration 3 years. Just before, 2 months before we installed in the space station, NASA announced they will cancel all the space shuttle. That means after 3 years, we will have nothing. And so I remember this, on April 16th, 2010, in the afternoon, I decided to change the magnet to a permanent magnet. So this magnet is still there, waiting to be used. The transition radiation detector identified electron-positrons and used 5,000 proportional tubes, 2 meters in length, centered to 100 microns. And filled with xenon CO2, it will last to 2040. Silicon detector mostly developed in Italy and Switzerland. We have 9 planes which measure the momentum and charge. Electronics. Since we use particle physics detector, so the electronics is much faster than what NASA provides. And also to avoid confrontation with export rules, we decided to buy the commercial electronics and test them in the electronics laboratory to make sure they're fast enough and reliable enough. So AMS on the space station produced 7 gigabit per second. And the signal is processed by 650 processors. These microprocessors are all specific design, and they have 2 to 4 redundancy, total 228,000 channels, and this process the signal to 10 megabit per second to white sand and to our control room itself. So the detector was quite expensive, but it was mostly done in Europe and China with strong NASA support. So in the United States, mostly MIT, and then there's Finland, Netherlands, France, Portugal, Spain, Italy, Turkey, Switzerland, Germany, Korea, China, including Taiwan. Let me make a comment. In space, because of the rotation of the sun and rotation of the Earth, the temperature changes quickly. So thermal control is one of the most vital things in space. And there's a university in Shandong province under Professor Chen Lin made the most important contribution to the thermal system, together with Professor Wei Xu, Sun Qie, and Cui Qi, and others. This group, like MIT group, had zero experience in space. But what I have decided to choose collaborators, not depend on their experience, but depend on whether they are interested in the project or not. So the detector has 5 kinds: TRD, time of flight, silicon tracker, re-emission calculator, and calorimeter. So different particles go through, leave different traces. And so we are measuring all the elementary particles and all the elements across the periodic table. This is the first time you can measure all of them. So we measure the momentum, measure the charge, measure the rigidity. Rigidity is a new term, momentum per unit charge. Measure the energy, measure the flux. So we have been in space now for 14 years. The question is, you have no shutdown. You have nowhere to check it. So how do you know your detector is still working? And so we have many redundant systems. So for example, the inner planes, layer 2 to layer 8, will have many lasers to check the relative motion. The outer planes, 1 and 9, they check with cosmic rays every 2 minutes. And so in 14 years, we see the accuracy 2 micron for plane 1 and plane 9. So it's stable to 2 micron in 14 years. In space, one of the most serious things, you do not know what's going on. At least for me, I spend enormous amount of time to see what could go wrong, or when we have to stop to check things. Once you know what's going wrong, you can correct it. Well, but if something goes wrong, you do not know you're going to make a mistake. So there are many physicists, Professor Chile Wen, Professor Wei Xu, Hang Chang is from Taiwan, and Professor Zhu Haoli, and Dr. Yi Jia, who used to be, most of these people used to be at MIT, and now many of them have to return to China. Cosmic ray was discovered in 1912. Cosmic ray experiment in the last 100 years typically has 50% error. Those are the data. And these are the theoretical models. So the model always agrees with the data. When you have a data 50% error, it's easier to confirm the theory. So this was before AMS. In the last 14 years, we have provided data to 1% accuracy and to multi-trillion electron volts. And so the yellow point is the AMS data with different elements. And they are in disagreement with theoretical models. There's no model who can confirm our data. You can adjust the parameter to agree with one, but the same parameter cannot agree with any of the others. And so the AMS data require the development of a new comprehensive cosmic ray model. Well, galactic cosmic ray, there are 2 parts. Primary, they are produced in stars and accelerated by supernova. And the secondary, They are produced by collision of primary with interstellar media. So measurement of cosmic ray nuclei flux are important in understanding of the origin, acceleration, propagation in the galaxy. The first surprise on the galactic cosmic ray is primary cosmic ray has two distinct class and totally independent from secondary. So primary cosmic ray, like helium, carbon, and oxygen, their absolute value is different, but their rigidity dependence is exactly the same. Similarly, for secondary cosmic ray. That means cosmic ray, actually it's very simple. They, even though it looks complicated, but they only have two classes. If you look more carefully, the primary class actually have a subclass. And so there's the light element, there's the heavy element. And secondary cosmic ray also have two subclasses. These are not predicted by any theoretical model, to my knowledge. So today, we have measured 250 billion events to provide precise spectroscopy of cosmic nuclei. So we measure hydrogen, helium, and the separation is 1 part in 10 to the 9. And between iron and cobalt, separation is 1 in 100 because the low rate of cobalt. All these cosmic rays can be separated into basic two classes. Two primary classes for the primary element and two secondary classes. It's really amazing how simple it is when you do them precisely. And this goes from 30 GeV to 3,000 GeV. So I want to mention we have many good physicists. Dr. Q Yang used to be MIT, now is one of them. Let me now measure the precision measurement of isotopes. Isotopes of particles with same charge, different mass. So we have a very precise velocity measurement device called RICH, and the velocity resolution is Z equal to 4, is 4 parts in 10,000 at the speed of light. So this is a very precise measurement of velocity. With this, you can distinguish mass. The first surprise is the origin of cosmic ray deuterons. Helium, carbon, oxygen interact with interstellar media, produce deuterons and helium-3. That was what everybody think before the OR experiment. Therefore, deuteron and helium-3 are both known to be secondary. But we found the flux of helium-3 increased to energy to 4 GeV and then progressively decreases. If deuteron is pure secondary, then the ratio of deuteron to proton must also decrease with energy, but they become a constant. So the velocity, so the dependence of proton over deuteron, proton over helium-3 are totally different. That means there must be something else besides secondary. It's not primary. But no one knows why it is this. We also measure lithium isotope. There are a lot of interest on lithium-7 as a primary component. And this is one of the models of lithium-7. And this is different from our measurement. We have not found any model can fit our data. And then there's a result on beryllium isotope. Beryllium has 3 isotopes, 7, 9, and 10. Stable beryllium-9 propagates through the entire galactic halo, and beryllium-10 decays to boron-10, and therefore the ratio tells you the length of the galaxy. This is our measurement. Fits one the model, shows the length of the galaxy is 3.7 plus minus 0.5 kiloparsec. This looks a good fit, but unfortunately, the same model does not explain other data. It's good for this data, but it's really not valid. And then let me share with you results on cosmic elementary particles, positron, electron, antiprotons. They can have only three sources. One is cosmic radiation interacting into interstellar media, produce positron, antiproton. Another is dark matter collision, produce positron, antiproton. Another is when pulsar, a rotating neutron star, produce positrons, but it does not produce antiproton. This is our measurement of positron spectrum. There are 4.5 million events from very low energy to 1,000 GeV. Cosmic collision is what you expected. Can I explain this low energy part? The question is, what is this? Why is there such a large axis? And also, it goes down. The most simplest explanation is this must come from either from pulsar, from dark matter collision, because these are the only two sources we know. But more important is the spectrum suddenly goes down. And so you have a cutoff at a very high confidence level. Nobody predicted that. So we'll continue the experiment to 2030, and so that the data in this shape will become data in this shape. This is the same graph, except from 0 to 200 GeV, it's a log scale, 200 to 2,000 is a linear scale. And so you can see the data agrees with the positron from dark matter collision, but you certainly cannot claim that. You need more data to make sure you have a better agreement, and you also should see the point without dark matter contribution, because the finite mass dark matter cannot produce very high energy positrons. So that is exactly what we're doing. Another unexpected thing is cosmic antiprotons and positrons. We found the measured positron, antiproton spectrum and positron spectrum above 60 GeV is exactly the same, the ratio is factor 2. So the identical behavior of positron antiproton above 60 GeV exclude pulsar origin positron, because pulsar does not produce antiprotons. Then there's a very important subject, and that is heavy antimatter. Matter is defined by its mass and charge. Antimatter has same mass but opposite charge. So the question is, where is antimatter star made of antineutron, antihelium, anticarbon, antioxidant? For this, you need a very precise detector to look for it in space. These are two antihelium candidates. So this is a bending plane, non-bending plane, in Cherenkov ring. This event have a charge -2 plus minus 0.05, mass 3.81 plus minus 0.3. And this one charge -2 plus minus 0.05, mass 3.15 plus minus 5.3. Just the opposite of helium-4. These events cannot be produced from cosmic calculations because these are rather high rate. So after 14 years, we have enormous amount of matter, electrons, protons, and nuclei. We have quite a bit antimatter, antiproton, antiproton, and positron. This can be explained from dark matter collision, from pulsar, or from cosmic collision. But the candidate of anti-helium cannot be explained by this. And these are very clean events, no backgrounds whatsoever. We are now looking for anti-carbon and antioxidant to ensure you indeed see an antimatter universe. Now let me touch upon a very important subject with the current NASA administration, that is long-term interplanetary exploration. Lethal cosmic radiation is approximately 300 grams. To survive a long-term mission for Moon and Mars require complete radiation knowledge being uniquely provided by IMS. So lethal cosmic radiation now is being measured accurately with rate, time dependence, energy dependence elements of periodic table. So IMS results are mitigating the lethal effect cosmic radiation for safe exploration of Moon and Mars. Cosmic radiation from galactic cosmic ray and the first around the Earth, the radiation in low Earth orbit from interaction with the atmosphere and trapped in Earth's magnetic field. Radiation in the interplanetary space on mission to Moon and Mars will lose the protection of Earth's magnetic field. In addition, there's radiation from the sun, called FCP. First thing we found, radiation is not a constant. This is an example of proton, or similar for all the elements. Hourly, from 0 to 6 to 12 to 18, every hour the radiation is different. And daily, every day, December 1st, 7, 15, 22, every day is different. And every year is different. And this is very, very important if you want to leave the vehicle, go out, you may want to choose this area, not this area. So cosmic radiation varies hourly, daily, yearly, and cannot be predicted by current model. And this is from SDIT of Chen-Ling and Wei-Wei-Xu. That is energy dependence of the electron flux over 22-year solar cycle. And this is high energy, gradually decrease with energy. You see the structure gradually disappear with high energy. And the dangerous region, it varies year by year, day by day, hour by hour. Even for the simplest thing, elementary particle, in interplanetary space over the 11-year solar cycle. You can look at the particle with same mass, opposite charge, proton, antiproton. Their functional dependence and function of time is quite different. For electron-positron, they are similar. For a particle with same charge, different mass, electron, antiproton, they are very different. The absolute value, of course, is different. It's the functional behavior. It's also quite different. But this, only the absolute value is different. The functional behavior is the same. And then there's positron, antiproton, for particle and antiparticle. But this is quite different, but this is the same. So this is a unique information for understanding cosmic radiation as function of mass, charge, and energy. This has nothing to do with the current cosmic ray model. Then there's a relationship between positron, electron, and proton. And this also comes from Shandong University. So what is the relationship, the daily rate at 1 GeV between electron flux and proton flux? In 2011, it's the red point. In 2016, it's in this relation. 2012, 13, 14, and then 15, 16, 17, 18, 19, 20, 21, 22. So it's a hysteresis. But for proton and positron, it's a linear relationship. Something totally unexpected. Then another curious thing is helium. Helium in low Earth orbit. In the energy range between 100 to 4,000 GeV over a large area of plus minus 35 degrees, only helium-3 exists. Helium-4 and helium-3 are in the outer region. So this is a very important curve. That is a summary of skin dose from different nuclei over the 11-year period. And so since radiation damage proportional to this square, so proton and ion have the same radiation dose. The lethal dose is about 300 rand. This is over 11-year period. This is the plot of sunspot for solar cycle 24, solar cycle 25. And so for solar cycle 24, in 2014, the polarity changes from negative to positive in solar maximum, in solar minimum, go back to solar maximum. And this part is remain to be measured. So at solar minimum, 3-year dose is 240 rand. The lethal dose is 300 rand. But this 300 rand is an estimate from Hiroshima and Nagasaki. And so this is very close to lethal dose. More important, which year you start really depends on accurate measurement of this. This is the first time made available. Well, now upgraded detector and the leadership of DESY Wang from IHAB. So in a few months' time, we'll put in another layer, come up with SpaceX, and then use a Canadian arm to take this out and use 4 astronauts to connect 74,000 channels to the electronics. Much of the detector were done at the IHAB and at the SDIIT under the leadership of DESY Wang. There was DESY Wang here. And they really did a very good job building this spectrometer. When we first went to space, Scientific American had an article about space station's crown jewel, about AMS. The discovery of the J particle 50 years ago opened a new realm of physics. Space is the ultimate laboratory. Space provides particles with highest energies. MS result required the development of a new model of cosmos. So thank you.
Okay, thank you very much for the beautiful lecture on modern experimental physics. So let's open the floor for questions.
I'm surprised no question.
Yeah.
Thank you for a beautiful lecture. It's very stimulating to see that there are so many experimental results which are not explained by theory. Could you maybe give us a hint or a guess where you think which ones of these most likely will have a chance of being explained first? Which ones of the experimental results that you have discovered that we know about that has the most likely chance of being explained by theory in the future?
I'm absolutely incompetent to do that.
Thank you.
Any questions? Yeah. 你们准备多点麦。
A student from Southeastern University. I remember you said to us that your experience is that you doubt yourself forever. Yes. So my question is, what kind of belief deeply in your heart that made yourself personally contribute to experiment physics for nearly 70 years? Yes. Thank you.
I did not understand the question.
Could you repeat again?
Yes, I should say it slowly. Yes.
No,
Yeah. Okay.
I did not understand.
Yeah. My question is, what kind of belief deeply in your heart that made yourself personally contribute to physics for nearly 70 years?
Why are you so enthusiastic about physics?
What do you want to?
What makes you to feel so enthusiastic? He asked you, why do you have so much enthusiasm? And what drives you to work so
I
hard?
guess I'm somewhat curious.
Other questions? Yeah.
Thank you, Professor. I have two quick questions. The first one is, how do you distinguish between cosmic background deuterium and this accelerated deuterium? The second quick question is...
One.
Okay.
Cosmic produced deuterium come from space.
Yes.
You can trace it because the detector is so accurate. You can trace it far 50 Earth radius away. Accelerator, you are within 100 meters from the accelerator. So no question to distinguish them.
Okay, the second quick question is, can AMS look at different directions in the sky? I'm asking because if we want to know whether it's the origin of that positron is from dark matter, we may look at towards galactic center or look against galactic center. And if we see a difference between the two, probably
Yeah.
that would be a more
Yes, there's we have a large angle, but you cannot look the direction because you do not know the intergalactic magnetic field. A charged particle bends in a magnetic field.
okay.
Therefore, you will not know.
I see. Thank you very much.
Other questions? Okay, if not, thank you very much indeed. Beautiful lecture. So we come back at 11.